you very much. It's a very pleasure to give lectures on my favorite topic. Thank you very much for the invitation. And this is going to be my first big lectures in Korea, so it's very, very nice. I wish I could have done this in Korea, but well, I'm Japanese, so like I should be able to speak Korean much faster than all other people, but still too much. Yeah. All right. So I'm supposed to give lectures on this equivariant and cohomology of toric manifolds. So here is my plan. So today I'll just give some basic, try to introduce what equivariant cohomology is and how, and in the end I want to stress that how you go and come back from ordinary cohomology of the manifold and the relation between equivariant cohomology and ordinary cohomology. Usually it's easier to calculate equivariant cohomology because it has this torus action, gives you some machinery. But then it's not really trivial how to come back from equivariant cohomology to ordinary cohomology, but there's some trick to relate those two things. So I'll do that today, and tomorrow is a big day, hopefully. I'm going to calculate cohomology and equivariant cohomology of toric manifolds. And the way I do is, first I calculate purely topologically what the equivariant cohomology is, and then I'll try to deduce ordinary cohomology of toric manifold from that computation of equivariant cohomology. And the very basic computation we have to do is establishing cell decomposition of the toric manifolds. Yep. And the third day, the third part, probably I'll spend all time on this number 2 part. But after that, I'm going to explain some general methods of computing equivariant cohomology and ordinary cohomology when you have Hamiltonian torus actions. And namely, it's called the injectivity theorem or Chan-Shell lemma or GKM description. And there's another thing is this Cowan surjectivity. So I'm going to talk about that general methods, and then I'm going to try to write this GKM description for toric manifolds. And this actually very instructive and helpful technique in other contexts. And somehow in the toric case, there's so many techniques, so many different languages to discuss what the cohomology is. So probably we don't really see this GKM description of the toric manifolds, but this actually tells you a lot of explicit understanding of certain classes. Like I can explain. So there is a generator of this equivariant cohomology. It's a quotient of polynomial ring. And what this generator corresponds to geometrically, and I can explain that by this GKM theorem. Namely, this codimension 2 submanifold, torus invariant submanifold gives you the generator of equivariant cohomology. And another thing is I can also discuss what the class associated given by the symplectic structure. The symplectic structure is, we discussed, it's a closed 2 form. So it defines a class in a Durham cohomology. And so it defines a class in a cohomology, and what is it in these descriptions. And then I can discuss that using this GKM description too. Yeah, so that will be the last goal of the 5 lectures. Okay, so let's start with this a little slowly, what the equivariant cohomology is. And so we were interested in some group actions. Group, say, action on the manifold. And when the group, say, compact Lie group acting on the manifold, and if it acts freely, it's the best scenario. When it acts freely, you can take a quotient, and the quotient space is again a manifold. So instead of looking at this group action, you look at this quotient space. Yeah? But when this group action doesn't act freely, the quotient space is not really a good space. So there's some kind of homotopical approximation of that quotient space, and that's called the Borel construction associated to a group action on a manifold. So the idea is really starting from discussing this universal principal G bundle. And let's just start with this topological group. Yeah. And this EG, BG, it's called universal bundle if it satisfies the following conditions, right? So EG, so basically this is a principal G bundle over some topological space, yeah? And EG has to satisfy this so-called weakly contractible. So I don't really care about this weakliness because most of the time it's just contractible. But technically when you start with the general topological group, this is the definition, weakly topological, which means that all the homotopy group is trivial. Yeah? And this happens when it's contractible, right? And that's one thing. And the second thing is, so as I said, this is principal G bundle. Okay, so this is just a definition, and I don't really say if this kind of thing actually exists for any topological group or not. But why do we define this thing? Yeah, and the theorem, it's not so difficult to prove from this definition is this. So basically, more or less, when you have all the principal G bundle over some topological space X, and let's take isomorphism classes of this principal G bundle, so divide by isoclasses, isomorphisms, right? And there is a one-to-one correspondence between maps into this BG. Yeah? So by the way, this EG is called the universal bundle, and this BG is classifying space. That's what people call. Okay, and then the name comes from this theorem, I think. Yeah. So for any principal G bundle, there exists a map from this base space into this classifying space, and let's divide by this homotopy. So the homotopy equivalence classes of maps from X into this classifying space, there is a one-to-one correspondence into equivalence classes, isomorphism class of principal G bundles. Yeah? And the way you do is, so if you have a map, yeah, say if you have a map from X to BG, it gives you a pullback maps, a pullback of the principal, pullback of the universal bundle. Okay? And this part is really easy because pullback of principal G bundle is a principal G bundle. But this direction is really the content of the theorem. You have to construct, for any principal G bundle, you need to construct a map such that the pullback of EG is the given principal G bundle. And then you have to show that that's unique up to homotopy. Okay? But that's what we have for this universal bundles. Okay? And so what about the existence? So maybe before we do the existence with the typical universal space, right? And I think it's actually enough to talk about UN, or maybe GLC. Okay? So what happens for the unitary group, the BG is called infinite Grassmannian of n-dimensional subspaces. So C infinity is C infinity, the infinite dimensional complex plane, and this is the space of all n-dimensional subspaces. Yeah. So you can think of this as kind of approximation by finite Grassmannians of n planes. Yeah. And what this universal bundle should be over this infinite Grassmannian, right? So the fiber of this principal bundle should be this unitary group. Right? So basically, you have a natural Hermitian metric on this C infinity. So like when you have this n-plane, you take a orthonormal basis. And on the set of orthonormal basis of n-dimensional plane, UN acts freely. So that gives you the principal G bundle over this infinite Grassmannian. So this is the space, a space of orthonormal basis. Yeah, maybe or maybe orthonormal, space of orthonormal set of n vectors in C infinity. Yeah. Okay. So this natural map from here to here, just look at the space spanned by these n vectors. That gives you a point in here. This is a UN bundle. And you can actually prove this EG is weakly contractible. And you actually be able to prove that there is a cell decomposition of this space, and there is this Whitehead theorem tells you that weakly contractible and there is a cell decomposition, it's actually contractible. So that's why, you know, most of the time we have cell decomposition and weakly contractible is actually contractible. Yeah. So this is actually contractible, e.g. contractible, and the action of the UN free. Okay, and there's analogous thing for GLC, and BG is actually the same infinite Grassmannian, and EG is just the space of sets of independent n vectors. Yeah? You're not taking a unitary basis of the n-plane, you just take all independent vectors, and that gives you a plane. And there, this G acts freely. So this is the real version, and this is the complex version somehow. Okay, being said about this, you know, the typical example of this universal bundle, and what happens to any compact B group. There exists EG. Yeah, and the way we do this, the proof is just a bunch of big theorems, right? The compact Lie group, it's actually a closed subgroup of GL to GL and C. Yeah, so this any compact Lie group G is a subgroup of GLN. Right? So we are looking for weakly contractible space where the group acts freely. So there exists the embedding of this group into the GL and C, and so the E of GL and C works for UN for this any group G. Okay, and instead of using E of GLN, you can actually use E of UN too, because UN is a maximal compact subgroup inside of GL. So you have this compact Lie group G inside of GLN that should sit inside of maximal compact Lie group inside of GLN, and maximal compact Lie subgroup of GLN, it's all conjugate to each other, so it conjugates to some UN inside of GL, so this G actually sits inside of UN. So from that theorem you can actually use not this one but this one too. But this one is sort of like compact version, and this is sort of non-compact version, so sometimes it's easier to use this. And it's very instructable to write down what the universal bundle for U1, a circle action, and that's what we are interested in these lectures. So, so E of U1, I mean, it's an infinite Grassmannian for one plane. So it's just CP infinity. Sorry, this is BG, right? And E of U1, and this is actually all the unit vectors in the infinite complex plane. Right? All the unit vectors of infinity. Yeah? And the complex analog to U1 is C star.
The BG is always same, or BG are different?
A BG? This and this are the same. And why they are the same? Is there maybe theorem saying that?
These are the same set.
Yeah, but is there a theorem saying that you have a complex Lie group and there's a maximum complex subgroup, the BG are the same? Yeah. Actually, this is not a coincidence because this GLN is homeomorphic to R something cross UN. So this is actually homotopic to this, and that actually tells you this has to be the same.
But the G is different to G and then
Oh, so EG, we can take the same. So for this G. Yeah, so G is embedded in GLN, right? So EG you can use these. But of course, if you're taking a quotient of EG by G, so these are different. So here, BG is this E of UN modulo G. And this is different from B of UN. Is that the question? Yeah, because this is E of UN modulo UN. Yeah? But now you're taking the quotient by subgroup G. So of course the quotient is different. Yeah. All right, so the C star case, B of C star, that's CP infinity, and E of C star, that's C infinity minus 0. Okay, and just for your knowledge, what happens to any topological group? And so for compact Lie group, we can just embed into GL or UN so that you can use the standard ones for the universal bundle. But for any topological group, actually there exists EG for any topological group G. And that actually goes back to like 50s by a paper by Milner. And actually you can just look at that paper to how to construct this EG for general topological group. So it's somehow I have never used any topological group. I only use torus, so I don't really know how to construct this, but it's good to know. Any questions so far? All right, so maybe, for circle action, the torus action will be, so if you add T is any n-dimensional torus, of course, the ET is going to be S infinity to the power of n, and BT is going to be CP infinity to the power n. Okay? And what happens to a cyclic group? So let's take Z2. So Z2 sits inside of a circle. Right? So you can use E of Z2, you can use E of U1, which is S infinity. Okay? And what happens if you take a quotient by this Z2 action? So Z2 action is this antipodal map of a sphere. Yeah? So this is actually RP infinity. Yeah? And if you take this Zn, actually I haven't really thought about. Is it like, I don't know the name for, lens spaces? Yeah, infinite lens spaces, that's what people call. But anyway, it's, we actually interested in those spaces too, because sometimes we have to calculate the cohomology of those spaces. Yeah.
So theorem is for any topology with G, right?
Yeah.
BG always exists.
Yeah. BG is just a quotient of EG.
BG exists for any group.
Yeah. BG, EG exists, and BG is just a quotient of EG.
For any one group.
Yeah.
Then you said for any one group, there is BG, right?
Yeah.
BG is like a quotient. For any group, there is not for any.
So I was thinking BG is just EG of the quotient of EG, but maybe not.
Not for friend group, not for any group.
And
BG. For any group? Well, then you put in the topology.
any topological group. Any topological. If you don't have a topology, it's going to be a discrete group, but it works for that too. Yeah. Okay, so so from now, I think we just define what the equivalent cohomology is. So the motivation was when a group acts on a manifold nicely, you just look at the quotient space. But when the group doesn't act on the manifold nicely, then the quotient space might be very, very bad space. So like, what can you do? Like, for example, calculating cohomology. It might be a little like unrealistic to calculate the cohomology of the quotient. So how do you replace the cohomology of the quotient? That's what this equivalent cohomology does. So basically, we define this. So G acting on the manifold. In this case, just topological group G acting on the topological space M. It's defined as the cohomology of this quotient. And this quotient is called sometimes homotopy quotient, or usually people refer to this as Borel construction of the manifold. So you take a direct product with EG and M, right? So M didn't act on M nicely, like freely. But EG, it's a contractible space, so somehow taking a direct product doesn't change much, right? And G acts on EG freely, so the quotient is going to be nice, principally, yeah? All right, so this is called a Borel space. And usually I write it as EG cross M, and then you little g below X, yeah? Okay. All right, so now we have a definition of equivalent cohomology. And we have to do a little bit of computation of the standard, cohomology of the standard spaces. So the typical thing is what is CP cohomology of CP infinity? Yeah. So this corresponds to the U1 equivalent cohomology of a point, right? Which is, so you take a U1 cross point, right? And on the point, the circle acts trivially, right? So E of U1 cross point and modulo U1. So this is actually B of U1. And B of U1 is CP infinity. Yeah? So let's calculate what the CP infinity is. So maybe before I actually write the cohomology ring, the CP infinity has a nice cell decomposition, right? So let's say the zero cell is 1, 0, 0, 0, 0, 0. Yeah, this is like infinite homogeneous coordinates. Yeah, you put 0 except the first one. Okay? So this is the 0 cell, and the 2 cell is you put 1 in the second coordinate, 0 everywhere else, and then you can have anything on the first coordinate. Right? And at this point, the second coordinate has 0, and this 2 cell doesn't have 0 on the second coordinate, so this is strictly disjoint, right? Yeah? So this is a point, and this is like C, right? For each complex number, you have a point in this, right? And this is 2 cell, and there is a 4 cell, a Z1, Z2, and 1. Yeah. So this gives you like a standard cell decomposition CP infinity. I mean, this comes from the standard cell decomposition of CPN. Right? Right, so from this, you already know that the cohomology of CP infinity, it has there's only one generator in each even degree. Yeah. And okay, so being said that, let me just cite a theorem from Milner's book, Milner and Stashev on characteristic classes. Probably you can find this theorem anywhere. So the cohomology ring of the CP infinity is isomorphic. I mean, it's exactly generated by the first term class of the tautological line bundle. Yeah? So what is the tautological line bundle? I mean, CP infinity is a bunch of lines in C infinity, right? So for each point on CP infinity, you associate a line which is itself, right? That's the tautological line bundle. So L is defined as, say, so this is the point in CP infinity, and so for each point, you look at the line. So, huh? Complex? Not compact, not compact. It's sort of limit of CPN. So of course it's not going to be compact at all. I mean, it's not finite dimensional. All right, so I mean, how do you write this L explicitly? So this Z, so let's say CP infinity is a quotient of S infinity, and S infinity sits inside of C infinity, right? And you have a unit vector in C infinity, and you look at the quotient by a circle action, right? This is the equivalence class, right? So take that point Z, and take that Z, and then scale that to get the line. So A is just any complex number, and that gives you a line over a point on C infinity, right? So let's take this L infinity, just lift this tautological bundle to S infinity. So this is just a pair of Z and AZ, and so Z is S infinity and A is in C. Yeah? And here on S infinity there is a torus action, I mean circle action, right? And that gives you So here you have U1 action, okay? And U1 action actually sends this ZAZ to, it doesn't act on the line, it just acts on the underlying space, TZAZ. Yeah, this is the action I consider, right? So with this action, you take a quotient, you get the tautological line bundle on CP infinity. Yeah? I was just trying to understand what the tautological line bundle on the CP infinity, right? All right, so now, somehow, this formula doesn't really help me when I compute things. Because, okay, so tautological line bundle is a very beautiful line bundle, but it's not really like a systematic definition of a lot of line bundles. It just gives you a single line bundle and everything is generated by this line bundle. Okay, but I want to know like how to construct other line bundles and vector bundles, whatever, to create all the classes inside of this CP infinity. Yeah. So for that, I actually use something different. So this is a little bit of a preliminary thing. So maybe I'll just make this an exercise. Yeah? It's about the torus and character of the torus. So there is natural isomorphism of Z module between, okay, before that, T is torus, and this frac T, that's Lie algebra, and there is exponential map, yeah, and T of Z, that's the lattice inside of the Lie algebra, which is the kernel of exponential map from the Lie algebra to the torus. Yeah? So T is usually, Rn. Right? It's the Lie algebra of the torus. It's Rn. And the lattice, it's a lattice sitting inside of Rn. Okay? Okay. So now, the exercise is dual lattice. So lattice is the kernel of the exponential map. And if you take the dual of that kernel, yeah, and it's also free Z module, right? It's isomorphic to the homomorphism from T to U1. This is called the character group, yeah? Character of this torus. And the way we do, I guess when you have a map from T torus to U1, you take a differential, and that gives you a map between Lie algebras, right? Lie algebra U1 is just R, so it gives you elements in the T star. And because it comes from a homomorphism from T to U1, it actually sits inside the lattice. Yeah? So that's how you get from here to here. But usually we identify a dual lattice and this homomorphism from T to U1. Yeah? Okay, so you have to actually look at this exercise and then work it out a little carefully. So this association you have to feel like very natural all the time. Okay. Right. So now. So I'm going to prove. So let's define a map from the symmetric algebra of the Lie algebra of U1 and dual and take a lattice. Yeah? So this thing is isomorphic to Z, right? The Lie algebra of U1 is R, and then you're looking at the lattice inside R, that's Z. So this is actually a polynomial ring. Yeah, symmetric algebra on this rank 1 lattice. That's a polynomial ring with one variable. And so this X is the canonical generator corresponding to X is just the identity map from U1 to U1. Yeah? So, I mean, this X is the canonical generator of the dual of the Lie algebra, which corresponds to the identity map from U1 to U1. Yeah? Okay. So I'm going to define a map from this polynomial ring to a cohomology of CP infinity. And how do we do this? So you send X to a line bundle Lx, which is defined by, you take S infinity and take a product with the representation associated to X. So this is just the standard action of U1. So on this C, U1 acts through this character, which is identity map. So it's just the usual representation. Right? This is a trivial line bundle, but there's an action of U1 both sides. So you take a quotient. Yeah? And then, so this is just line bundle on CP infinity. So you send it to the first Chern class of this complex line bundle. Yeah? So this defines a natural ring homomorphism from polynomial ring into cohomology of CP infinity. Yeah? So for example, if you take a 2x
What was CX?
CX is just CXZ. So there is an action of U1, right? So T acts on this Z by X. But X is now identity map. So maybe I should say X of T multiplied to Z, which is just T to the Z in our case. Yeah, so, okay, let's not confuse too much. All right, so this actually defines a nice homomorphism, ring homomorphism from polynomial ring into this. And we already know that the right-hand side is a polynomial ring. But the only thing is I don't know what this C1L in terms of this X. Yeah? But okay. So now let's look at this L infinity. It's right here. L infinity is actually equivalently isomorphic to S infinity cross C of minus X. So minus X is basically the inverse map. Yeah, so the elements T goes to T inverse. Okay, so that's the action of a C1 on this C of minus X. This minus X specifies how U1 acts on this C. And we can show that this is isomorphic to this because, and this is actually U1 equivalently isomorphic. Yeah? So Z AZ goes to Z and A. Yeah? And this certainly, you can recover this from this, right? You have A and Z. You map it to Z and A times Z. Yeah? So this is certainly homeomorphic. But what about the action, right? Action is more subtle, that's why I had to put minus X here. So the action of T here is TZ and AZ. Yeah, remember? That's how I define the action over here. And that's how I recover the tautological line bundle on the CP infinity. Right, on the other side, yeah, here, T acts on Z by just multiplication, but T acts on this A by T inverse. That's why I put minus X, right? Yeah? Right. So this, yeah. A. So now I think this works, right? So I guess use this map, right? A and Z goes to Z and AZ, right? So this goes to TZ and TZ and T inverse A, which is AZ. Yeah. So this map is actually T equivariant isomorphism. Yeah. So this means that L is isomorphic to L of minus x. Yeah. So this means that C1 of L is equal to minus x in under the map. Under the map. Let's call this map phi. Yeah?
Where does the x square go?
Huh?
Where does the x square go?
X square.
Yeah.
I think x square goes to Lx, direct sum Lx. Yeah, I think. I always get confused. This goes to, I think, Lx plus Lx, and 2x goes to Lx squared. Does this make sense? No, sorry. 2x, so this is Lx tensor Lx. Yeah. It's okay, right? I think.
And then they can move on to take a CD1, no, not C1, right?
So this is not the line bundle, so I don't take the C1, but this goes to C1 of Lx tensor Lx. That's just the tensor product goes to a sum in the term class, right? Okay? So what does this say? So minus x goes to the generator of the cohomology ring of CP infinity. So this phi is actually an isomorphism. And this is actually better description of cohomology CP infinity because you can create so many different line bundles. Yeah? Okay, and that's going to be a lot useful in the equivariant geometry of symplectic manifolds. Okay. So now understand, this is really a basic sort of things you have to go over once in our life, right? So now we have better thing. The cohomology of CP infinity is actually a cohomology of a polynomial ring with x. X corresponds to a generator of the Lie algebra, dual of the Lie algebra. And somehow it's easy to generalize what we have, those maps and this isomorphism. When you have, so say T is m-dimensional torus, right? And let's say the dual of the lattice, the kernel of the exponential map, dual of that is spanned by x1 through xm. Then the cohomology of BT. So BT is now CP infinity to the power of m. Okay? And there's a canonical isomorphism from this to the polynomial ring in m variable. Okay? And the way we associate, that's very important. You take xi here. Right? And xi goes to this Lxi, which is Et cross C of xi. Yeah. So now you have to look at this xi as a map from T to U1, right? Corresponding to the dual order lattice under this exercise. Yeah. So basically, if T is actually direct products of U1s, this xi corresponds to just picking up that particular ith component to act. Right? And then use that action and take a direct product. You take a quotient by the torus, and that gives you the line bundle corresponding to this character, and then send it to the first Chern class. Okay, and that gives you canonical isomorphism between cohomology of BT and the polynomial ring. Right, so now we have this equivariant cohomology, right? So the first property is this equivariant cohomology is a module over BT. Yeah? So it's a module over a polynomial ring. Yeah? And that comes from this map EG cross GM, and if you project to the first component, it gives you a map to BG, or I should say G torus now. Yeah? I don't really care compact Lie group in these lectures. So it's a projection to the first factor. It's a map to BG, and you can just use the pullback map. Pullback map is the cohomology of BG to equivariant cohomology. And this map defines the module structure on the equivariant cohomology. And it's actually both of them are ring, and this is a ring homomorphism, so you can also say this is a ring over polynomial ring. Yeah? And so there's this xi on the BG side, and that goes to xi here. Actually, xi multiplied to the identity elements in the equivariant cohomology. Yeah? What is this? Yeah? So the xi in the BG side, it was the first Chern class of this line bundle defined by this character. What about this xi sitting inside of equivariant cohomology? You know, line bundles, pullbacks, right? So you have a LXI here, okay, and you can pull back this line bundle to the line bundle over this Borel space, right? And that will give you this xi. Yeah, that's the property of a Chern class, right? Chern class pullbacks to the Chern class. Yeah. So, but what is it? It should be. So you have this EG cross M and cross C of xi, and then you divide by D. Yeah. So the LXI, that's defined by this, right? So I should replace this G by T all everywhere. It's confusing. T. I wasn't talking about the general Lie group. So here is the LXI. And when you pull back this line bundle to Borel space by this projection, that naturally gives you this. And that's something you have to check, but you know, I'm telling you the truth. You have to check it by yourself, right? So it's good, like this algebraic structure, the module structure of the polynomial ring, we have a geometric representation, presentation of the classes, yeah? Okay. Any questions so far? Okay, so that's about enough for most of the things, but I want to mention a little bit. All right, so I want to talk about a little bit of a free action and locally free action. So when G acts on M freely, Yeah? So let's look at this map, EG cross the Borel space, and let's take a projection to the second factor, right? So it goes to this. Yeah? And now G acts on M freely. What's the fiber? Yeah, fibers are just EG, right? You're taking a quotient by this diagonal action, but G acts on M freely, right? So you can recover everything in the fiber. And EG is contractible in nice cases, right? Let's just say G is compact Lie group. In that case, EG is always contractible, right? So the fibers are contractible. So the cohomology of this and cohomology of this, they has to be the same because you can just deformation retract all the fibers to the base space. Yeah? So with the G coefficient, it's isomorphic to the cohomology of the quotient space. That's reasonable, right? So somehow the equivalent cohomology, it's the same as calculating the cohomology of the underlying the quotient space. Of course, when G acts on M freely, because that's when we wanted to generalize, right? So what happens to G acts on M locally freely? And I think there are some people calling this almost free or whatever, and I know that the quasi-free is completely different, but locally free means that any point, the stabilizer, so all the group elements which stabilize X is finite. Yeah? So that's the meaning of locally free action. And in this case, let's look at the projection map. Now, G doesn't act on M freely. So if you look at a point in the quotient space, and if you look at the fiber, how does it look? Right? So there is a stabilizer. It's a finite group, but there is a stabilizer. So when you look at the fiber of this projection map, there are things in EG which couldn't be separated by group action. So I don't know if I'm saying correct, but basically the fiber is EG modulo the stabilizer. Yeah? Does that make sense? And somehow I couldn't really find a good reference for this fact, but if all these fibers are just the quotient of contractible space by finite group, right? So in this case, what we can say is, of course, the cohomology of this space and this space are different, but as long as you work over Q coefficients, they are the same. So instead of using a Z coefficient, take a Q coefficient, and then this pullback by this projection makes an isomorphism between the quotient space. Yeah. So the difference between this space and this space, the fibers are contractible space by quotient by a finite group. In this case, the cohomology only differ by torsion elements, these torsion elements. And I just can't find a good reference for this, but it's just my ignorance. So if you know any reference, please let me know. Huh? Transformation group?
Transfer map.
Transfer map. Transfer map is push forward map, right? Oh, well, okay, yeah. But yeah, so please give me a reference if you know one. But it's true. Huh?
Maybe in one of Siegel's papers, Graham Siegel.
Okay. You tell me the paper later. Okay, but it's okay. And I know it's true. I don't know. Like in mathematics, like you never say it's true unless you can prove it, right? But there are so many things I have to say it's true, but I haven't proved it yet by myself, right? I know the reference, I know this mathematician said it's true, and this kind of trust you have to use. Sometimes you don't trust your friend saying, you have to ask him to prove it, but well, I think I know enough number of people saying this is true, and yeah, okay, but it's true.
Can you describe the homology and the relationship between two homology and downstairs?
Here?
Yeah.
This?
Over Z.
Over Z?
Yeah.
Yeah, so that's difficult. I don't know. It's actually, so, okay. I'm working in like Toric topology, which is like you study the space with torus actions. But I started with like studying orbifolds. So I was learning like with a lot of pain, I was learning stack, language, groupoids and all these things. And now I work in a Toric topology, and people have been working on calculating the cohomology of this quotient space with the Z coefficients. But then, you know, things works only if you work over Q. I see so many theorems saying that, you know, this theorem works over Q. But then now I know what I should calculate with G equivalent cohomology. Like even if G acts on M freely, don't look at the quotient space, look at the equivalent cohomology. And this is nicer because M is manifold and then G is just a torus sometimes. And I look back all these theorems which were written in terms of, you know, Q coefficients, and some of them can be actually said with the Z coefficients if you take this definition, equivalent cohomology. And that was kind of nice for me. good to know. Right? But it's actually, so now we sort of know that, you know, it's easy to calculate equivalent cohomology because you're just dealing with a group action with a manifold. But the quotient space is a singular space, it's harder to calculate. And if I know the relation, exact relation between this and this with the Z coefficients, that'll be great, right? I know how to calculate this, and people wanted to know this. If you know the relation from here to here, that'll be great, but I don't know. And it seems it's really a difficult question, but just the fiber is this. So if you are some experts in this kind of pseudo fibration, you might figure out what to do for this from that. Okay, so I have maybe 10 minutes or something? Yeah. All right, so now let me briefly discuss what the relation between equivalent cohomology and ordinary cohomology. Yeah. So let me just state the theorem. So somehow, say M is a closed manifold means that it's compact. A compact and no boundary. And I think when Eugene said compact symplectic manifold, it's actually compact without boundary. Yeah. So like some people who care about these boundary things, people usually say closed instead of compact because sometimes people assume that there might be a boundary. But in our symplectic things, usually we don't have boundary. So he said compact and no boundary. Yeah. Okay. And then I say I just combine this compact and non-boundary closed. So yeah. Okay. And orientable. Okay. And the symplectic manifold is usually, a priori it's oriented because symplectic form gives you a volume form, and volume form is a nowhere zero section of the orientation bundle. Yeah. So it's naturally oriented. And manifold. I think that's enough for this. Right. So in this case, when the odd class vanishes, this is ordinary cohomology. If odd class vanishes, and this happens a lot of time in when you have symplectic structure with Hamiltonian actions. Yeah? And I'll tell you why later. And also, but if you don't have compactness assumed, then even if you have symplectic manifold with Hamiltonian actions, you could have odd degree. And also, if the manifold, symplectic manifold is not actually a manifold, it's actually an orbifold, then there will be a lot of odd things too. Yeah? But in nice cases, I'm saying compact Hamiltonian action on the symplectic manifold, in those cases, usually odd class vanishes. And in this case, what happens is the equivariant cohomology with the z coefficients, it's actually a free module over the polynomial ring. And the basis is given by the ordinary cohomology. Sorry, I forgot to put the torus action there. So the M is a torus, it's a closed oriented manifold with a torus action which preserves the orientation and stuff. Yeah? Smooth action. And when the odd class vanishes, then the equivariant cohomology is actually a free module with the basis this. Right? So what does this say? So this is it's not really easy to find out. But usually this is done by establishing the even dimensional cell decomposition, as we did for CP infinity. Yeah? And that tells you there's no odd class. Right, so in that case, even though we don't know anything about the cohomology, we know that the equivariant cohomology is a free module with the basis in HM. Right? And on the other hand, I mean, this isomorphism actually tells you that the ordinary cohomology is actually given by equivariant cohomology, right? So if you tensor Z as a module over the polynomial ring, so the polynomial ring acts on Z trivially, like all the parameters acts on Z trivially. So if you kill, basically this tensor product gives you the killing of the variable inside of equivariant cohomology. And then it recovers ordinary cohomology, the basis of this free module, right? So what I'm saying here, this consequence of this theorem is that if you know how to calculate T equivariant cohomology explicitly, and you know that there's no odd class, right? Now you kill all the variables coming from this polynomial ring, which represent the first Chern class of the line bundle, right? If you kill those Chern classes, it recovers the ordinary cohomology. So this is one piece of information you have to find out from the ordinary cohomology. But from that, there will be a great technique to calculate T equivariant cohomology very explicitly. And then that actually gives you an explicit description of ordinary cohomology. That's the storyline. Yeah? And this is not really important for now, but the sort of the inverse of this implication is also true. Say the fixed point is not empty, and the equivariant cohomology is free over BT, the polynomial ring, then the odd class vanishes. Okay? So somehow, if you happen to know that there is no, there is a fixed point, non-trivial fixed point, and, oh actually, sorry. No, the isolated. So if actually the fixed points are finite points in this compact manifold, and if you happen to know that T equivariant cohomology is actually a free module, then you already know that the odd class vanishes. Yeah? And it automatically gives you this decomposition. Yeah?
The twiddle up there is not a thing, right? It's modules.
So this one actually uses Roulet-Hirsch theorem, right? And Roulet-Hirsch is not really. Wait. No. This is actually a ring homomorphism. Yeah.
Modules.
This is module homomorphism. But it's not ring homomorphism. Yeah, that's somehow I got confused too. But really?
M is finite tenor, so if the degree of X prime part is positive, then it is always neutral.
Oh, I see.
And equilibrium homology,
Yeah, that's true.
there's no
Yeah. Well, I have to, yeah. So it's safe to say it's a module homomorphism. That's always like Ray-Hirsch. When you apply Ray-Hirsch, you always say it's a homomorphism of modules. But I was thinking maybe it's a ring homomorphism, but okay, I will be safe not to say much. Okay. So maybe I should have 5 minutes or something. Okay, now so let me explain why I'm interested in this locally free action, right? And it's very touchy issue. Like I don't want to get into all definitions and theories of orbifolds, but locally free action of a compact Lie group on a manifold, it automatically gives you an orbifold, right? So then it gives you something called orbifold. So the bracket means it's a pair of topological space, which is the quotient space, together with orbifold structure. Yeah? So this orbifold structure, there's many different ways of saying it. One, chart, right? So orbifold chart. Yeah? The orbifold charts on this thing, so basically you have an underlying topological space, you look at the open covering, and in each open set you have this orbifold chart. And orbifold chart is supposed to be a Euclidean space modulo finite group. And how do you get that from this locally free action? You actually use this slice theorem. Right? So take a point in this quotient space, and the neighborhood. There exists a neighborhood of this is isomorphic to the quotient of. So you look at the tangent space of X. X is up some point in this upstairs before you take a quotient, and you look at the top tangent space. Right? So when you take a quotient, you have to kill by the direction of the action of the Lie group. Right? So you take a quotient by the tangent space of the orbit. Yeah. So this is somehow gives you the tangent direction in the orbit space. But wait, there might be some stabilizer. Yeah? So there is some extra action of stabilizer, which is finite group. Yeah? So this gives you the local chart, orbifold charts, when you have this locally free action. Yeah? So that makes sense, right? And forget about all these equivalence class of orbifold charts, compatibility of charts, but this gives you a local charts. Yeah? That's one way of looking at orbifold structure. Right? So this certainly more than the underlying topological space, right? As a data. Right? It gives you this chart, which is extra data to the underlying topological space. So that's why we have to make a difference between with and without the brackets. Okay? And now, number two, groupoid. There is so-called the action groupoid. I don't know which direction. Yeah. So there's a way to look at the orbifold as a groupoid. Yeah? It's the Morita equivalent class of a groupoid, which is proper and et al. And this action groupoid belongs to a Morita equivalent class of propanetal groupoid. So whatever. But if you study this groupoid, you are studying the orbifold, number 1, 2. Yeah? And third way is very intrinsic, abstract, but it's very clean-cut definition of what the orbifold should be. That's a stack. Huh? No, it's just it's my notation. I usually use G acts on M, and it's an action groupoid. So this gives you a space of arrows. This is the object, and because G acts on M, it's called action groupoid. So that's why I just put a little circle here. And so it has nothing to do with the mathematics. Okay, so the stack is just like a very sophisticated way of defining what the groupoid is, and it's a category. The object is, it's a principal G bundle over some space where the equivariant map into M. Yeah, category. Yeah, but whatever, right? So the thing is, I want to convince is that when you have this locally free action, it gives you one orbifold. Yeah, but somehow when you go from here to here, you lose a little bit of information. Yeah, if you go all the way to M mod G, you lose a lot of information. But you stop at the level of the orbifold, you only lose a little bit of information. Yeah? So the thing is, this orbifold, you might be able to write down this orbifold as a global quotient by a different pair of group and manifold, G prime and M prime. So that means that you're losing some information. Yeah? No? You're not losing any information. You are not losing any information. Yeah. Okay. So I mean, are we not? So I guess the information is not lost. So that's why it's very like you can come back and forth. Right. Anyway. Right. So what should we do with the equivalent? The cohomology of an orbifold, right? And it's actually a space, underlying space, together with some extra data. So you could define as the cohomology of underlying topological space. That's one way. But now, when you look at the cohomology of underlying topological space, you're losing the information about the orbifold structure. Yeah? So, like for example, if you look at the point mod G, yeah? And this is really a trivial orbifold, right? Finite group G acting on a point trivially, but still a quotient of quotient by a finite group, and the underlying topological space, and this is just a point. Yeah? You don't remember the group G at all. So somehow this is not really a cohomology of the orbifold. What we can do is equivariant cohomology. So this I define the cohomology of this orbifold as equivariant cohomology when it's written as a global quotient by a Lie group. And cohomology. You can write it as a global quotient if it's an effective orbifold. Effective orbifold means that there is no global stabilizer.
And this is unique?
Not uniquely. Not uniquely.
This will be independent on G.
Yeah, so that's actually a good question, right? I'm choosing one presentation of this orbifold, and that's the information you lose when you go to orbifold. This choice of presentation. I guess that's what I was saying. So you have to choose this presentation of the orbifold as a global quotient. But what happens if you choose a different presentation? And they actually give you the same ring canonically isomorphic. That's a theorem. So this definition is independent of the choice of the presentation of the orbifold. Yeah? But actually, it's not really difficult once you have a correct, easy definition of cohomology of orbifold. Yeah? Okay, so that's why I was interested in locally free action too. Instead of looking at the quotient space, you look at the equivalent cohomology of the locally free action. Yeah. All right. So one more thing. I wrote up all the lecture notes already, and I will upload that PDF file to some website, maybe my website used a long time ago. So you can access to it, and then you can, and all the references and details are there. So please take a look at after the lectures, maybe before the lectures. Thank you very much.